This chapter, called Balls and Bins, is a slight digression from what we have been doing so far. So now we are not going to learn a new technique or a new trick. Instead, we are going to see how the same setup of balls and bins actually gives rise to so many different answers depending on what restrictions we put on the problem. The setup is that you have n balls and you have m bins, and you need to count the number of ways of putting n balls in m bins. That is always the goal. We are always trying to count something, and in this case, the number of ways of putting balls in bins. Now we're going to start putting restrictions. Okay, so the first thing, and I'm just going to go through this table that the book gives, because this is not a general theory. We are just doing some specific example, that is balls and bins. And this table is not comprehensive. There are many more cases that are not covered in this table. So you shouldn't think that this entire chapter is about this table. No, this table is a part of this chapter. You can make a much more complicated question, and you have to work out very deliberately how to solve that question. Okay, so the first thing is, on the balls, we have two possible restrictions or two possible adjectives I can put. The balls can be either distinguishable or indistinguishable. Distinguishable means that, let's say the balls are all numbered, like on a snooker table, the different balls have numbers on them, so they look different. Indistinguishable means they all look the same. Like, let's take a golf ball. Say you have hundreds of golf balls. You can't really tell them apart. Similarly, for bins, we can have the same restrictions. You can have now for the bins, we will have restrictions which are numeric in nature, and we'll come to those in a minute. Okay, so let's start with indistinguishable case, because that's what the book does first. So indistinguishable is the entire first row. And if you'll notice, what indistinguishable balls is doing for you is it's always doing some kind of combination. That is, the order does not matter. And that is, I'm doing some kind of combination. Okay, so that's the first thing. As soon as you see indistinguishable balls, you should think of combinations or something where order does not matter. Now, what are the possible things I can do with the bins? I can have no restriction on the bins, but the bins are all distinguishable. So the bins are all different. And this is the example we did in the previous video. This was counting multisets, for example. So this particular square is multisets. Remember, indistinguishable balls in different bins. Okay, now and there are no restrictions on how many balls go in how many bins. That's why we have this number. But now I'm going to put a restriction, and that restriction is at most one ball per bin. So I have lots of bins, and this means that, I'll expand this. This means that a bin is either empty or contains a single ball. That's it. So how many ways are there for me to put balls in bins such that each bin is either empty or contains a single ball? Well, if you think about it, what we are doing is we are just choosing which bins to put the balls in, and the rest will be empty. Okay, and so this is number of ways of choosing which bins to put the balls in. And how many ways are there to choose which bins to put the balls in. Well, there are m bins and there are n balls, and so this number is exactly m choose n. Okay, so if I put the restriction at the most one ball per bin, I just get back m choose n. Now the third thing they're doing is same number of balls in each bin. So I have some bins and I have some balls that I can't distinguish between. So let's say I have like 10 bins and I have 50 balls. And I want to put the balls in the bins, and each bin gets 5 balls. Well, the balls are not distinguishable. There is nothing for me to do. I just take any 5 balls and put them in the first. I take any 5 and put them in the second. I take any 5 in the third, and the remaining in the fourth and the fifth. And so there is exactly one way of doing it. And that's why you get the number 1. Okay? So there is no choice here because the balls are indistinguishable, and I'm telling you how many balls go in each bin. So the last one is trivial. There is nothing to do. Now, when you have distinguishable balls, let me highlight this. As soon as you have distinguishable balls, you should think that the order matters. Because now the balls are numbered 1, 2, 3, 4. So how you deal with the ball matters, in which order. And so you are doing some kind of permutations. Okay. So let's look at the first case. Now I have m bins, and I want to put balls in these bins. But now it does matter where the ball number 1 goes. Like it can go to the first bin, or it can go to the second bin, or it can go to the third bin, or it can go to the fourth bin, and so on. So for each, in this case, for each ball, I have a choice of m bins. Okay, so the ball number 1 has m choices. Then the second ball has m choices. Then the third ball has m choices. Okay, and this is only meaningful because the balls are all different. So I can make sense of the first ball, the second ball, the third ball, and so on. And this is something we did long time ago. This is the product principle. You're making one choice for the first ball, then you're making a choice for the second ball, then for the third ball, and so on. And so this is m times m times m. And how many choices you're making total? You're making n choices. And so the number, a final answer is m to the n. That's where that number comes from. Okay, now remember that at most one ball per bin means either a bin is empty or it's full, or it contains one ball. So all you're doing is you're choosing which bins to put your balls in. But now here's the thing. The balls are distinguishable. So I need to make the choice one by one. So what I'm doing is choose a bin for ball 1. Okay. Then I choose a bin for the second ball, but that's different from the previous one. Choose a different bin for ball 2. Then choose a different bin for ball 3, and so on. These kinds of problems we have done before. For the first ball, I have m choices. M is the total number of bins. For the second ball, I have one less choice, so m minus 1 choice. For the third ball, I have even one lesser, so m minus 2 choices, and so on. And that is nothing but p m n y n, because I have total n balls. And that's why when you have to put one ball, at most one ball in a bin, and all the balls are different, we get PMN. Finally, suppose you want to equally distribute the numbered balls in different bins. So suppose, very simple example, you have 4 balls and 2 bins. So I want to say I want to put 2 balls in this bin and 2 balls in this bin. How many ways are there? I claim that it's 4 factorial over 2 factorial, 2 factorial. And that's where this is coming from. Though this last term should remind you of n factorial over n1 factorial, n2 factorial, and 3 factorial, and so on. And why is it this number? Well, what I'm doing is I am just arranging the balls in an order. So I'll take these n balls and I put them in some order. So that's the top number. Okay, then I'll take the first n by m balls and put them in the first bin. Then I take the second n by m balls and put them in the second bin. Then I take the third slot and put them in the third bin, and so on. So that's easy. But now here's the problem. Let's say I had a ball number 1 and ball number 2, and both of them went in the first bin. But now if I had ball number 2 first and then ball number 1, and I put them in the same bin, I get the same distribution of balls. So what the problem is that the internal distribution of balls does not matter. Similarly, the internal distribution in the second bin does not matter. Similarly, the internal distribution in the third bin does not matter. And that's why I'll write this as follows. Put the first n by m balls in the first bin. Put the second n by m balls in the second bin, and so on. But then the order inside each bin does not matter. And each bin contains n by m balls. And so you divide by n by m factorial, and then again n by m factorial, and then again n by m factorial, and so on. And the total number of bins is m. Sorry, this is slightly badly written. So divide by n by m factorial for each bin. And this then gives you n factorial over n by m factorial whole to the m. So this is the derivation of this table in the book.